good with this.
Okay. Stand here.
Yeah. This camera is recorded. Oh, yeah, that's great.
Okay.
All right. I thought I would get some little extra light, just for everybody to see my face. Does the hair and everything look okay? I'm not. I'm
kind of
Or shall we do? How much time do I have?
like 40 minutes.
40 minutes?
30 minutes plus some question and answer. Like 40
Okay. Can I do like 10 minutes of some dance or?
It's up to you, guys.
It'll be entertaining, right? Stage is mine. Okay, entertaining, right? It will be if I do a little bit of dance, some stand-up comedy. Is that what you guys expect here? No. I mean, even if you had expected that, I'll be really lousy in doing it. Okay. So, still I'm doing it. Why? Two things. I wanted everybody to get engaged, right? First thing. Second thing, I wanted you to understand these two problems that I talked about right now. One, me doing a dance, stand-up comedy, or anything like that, which is very entertaining, by the way, is not what you expect here, right? Second, I'm lousy at it. You won't accept it. Many of you have paid 500 rupees to come here on your Saturday afternoon where we could have slept nicely after a good meal. But you didn't do that. You come here. I'll be wasting your money. And more importantly, your sleep, your efforts, and everything that you spent to come here. Keep these two things in mind because this is the crux of the presentation that I'm going to do. Two things. One, no wasting resources. Two, everybody should do what they're good at. Right? Let's start the presentation. All right. Yeah, we can turn off the lights now. Don't have to see me. All right. All right. So my topic today is computational storage for next generation AI. Right? Very heavy subject. I am pretty sure that many of you are not even aware of what is computational storage. I am not aware of AI. Right? But I'm still going to do it. The whole idea is that you guys are going to ask questions to me and I'm going to learn. And we are all here to learn because AI means learning, right? Let's do that. All right. Very first thing that I'm going to talk about is the problem with AI. We have been all using OI. Do you know what is OI? OI is original intelligence. In here, right? What are we talking about is AI. AI has got a big problem compared to OI. What is the big problem of AI? How many of you watch Star Trek? Star Trek, Captain says, Scotty, I need more power. Every episode of Star Trek, right? This is exactly what today's AI and hyperscaler centers are. The CIOs are talking to their team. This is exactly what is happening. We need more power. You know how much power our brain takes? 12 watts. How much power does a simple single NVIDIA GPU H100 takes? 700 watts. There goes the comparison. 12 watts versus 700 watts. So how many of you think that AI is not going to survive because it's taking so much power? You're all wrong. It's already there. It's taking 700 watts power, one GPU. And in a typical medium-sized data center, you would have 10,000 GPUs. Medium-sized data center is taking 7 megawatts power. A large-sized data center is taking so much of power. You won't believe in Northern Virginia, where they have quite a few data centers, hyperscalers. Today, their power consumption just by the data centers is 3.4 gigawatts, which is equivalent to 4 nuclear reactors supplying power. Now you talk about power, that's how it is. By the way, just count the amount of money it takes to supply a power like that, right? So coming back to the power part, while the brain does look like very efficient, let me tell you, the Chat GPT takes 1,000 times less power to create one page compared to human being. That's power efficiency. And since I learned this while doing this presentation, I almost stopped using my brain. All right. So let's come back to other problem. Power in absolute term is a problem. Let's come to another type of problems that we have in scaling the AI infrastructure. It's all related to power to start with. Bigger than power is the problem of called power density. I think Mr. Sanjay already talked about it, right? The problem at some length, right? And I'm going to put it more in terms of data, is that GPU systems are usually taking almost 10x power of a CPU system. So if you take a same rack where originally it was CPU and now it's converted into a GPU rack, it's going to take 10 times more power. So for example, one rack was taking 10 kilowatts of power, now it's taking 100 kilowatts of power. It's not making sense right now. And everywhere where in the same space you are going to consume more power, you are going to generate more heat. It's called with more power. You know, it's a dialogue in which movie?
Spider-Man.
Spider-Man. Yeah. Spider-Man says, with great power comes great heat. Great heat, right? And that's where what you need is cooling. The cooling levels have gone to such an extent that in today's data center, 40% of power is taken by GPUs. Another 40% of power is taken by cooling. Only 20% of power is left for everybody else. Think about it. It's really becoming unfair, right? But that's what it is when it comes to challenges of AI infrastructure. However, we need to come out of this, as I told you, right? All said and done, ChatGPT is still working much more better than our brains. So we have to start solving the problem for ChatGPT rather than solving the problem for our own brains. Anyway, it's very difficult to solve the problems which are here, right? So what we really need to try and do as part of solving this problem is try to increase or rather make it efficient how it can do the same job in less power, right? Rather than just thinking about the absolute power. However, there also the AI is consuming a lot more power. So ChatGPT query, for example, consumes about 10x power compared to the same query given to Google. Please don't switch to Google still. We are already on ChatGPT from Google, right? We are evolving. So still people are going to move more and more to ChatGPT and other engines for their queries and search. Why? Because they are much more efficient. All right. Now, as I told you, the data center power constraints are becoming harder and harder. Almost all the data centers today are running at their max power capacities. In Virginia and California, the problem is that there is so much power consumption by data centers that the new data centers are getting delayed. They don't have power. The utilities don't have enough power to supply to them, right? And the predictions are that the power consumption in next 2 years is going to double the way it's been used by these data centers. And it's already doubled today compared to 2022. So every 2-year doubling of power is not sustainable, right? So these are the challenges for scaling the AI infrastructure. On top of that, which is where the Indians care it most, right, is it takes a lot more cost compared to the other data centers that you would make, right? Also, scaling them, for example, putting more GPUs in the same rack is becoming a lot of challenge, specifically from software architecture and so on, right? And also the other components which are used in the same rack, they're not scaling. They are not becoming as better as GPU because everybody is focusing on GPU, right? So GPU is going ahead in the race. At some point of time, we'll realize that other components also requires a lot more attention, right? So these are the major issues for AI. Now let's look at how storage is being used in all of these AI-based data centers? Let's first understand the storage as a use, how it is being used in AI lifecycle. So I have simplified the whole thing for everybody to understand, right? We are all laymen. I'm assuming that I'm layman, right? When it comes to AI. So AI lifecycle has four major components. The very first component is data collection, right? Where what we are doing is we are collecting data from all different sources and then first store those data. This means, and usually some of this data collection or the overall data that is collected for AI to work is in petabyte scale. Such a large data set you have to store, and when you need it, you have to get it back because you're going to start a whole AI cycle, right? So this means the very first stage requires a large storage capacity and a lot of write performance. Because if you cannot write this much of data quickly, there are going to be other challenges, including power. Then the second part of the AI lifecycle is data curation, where what you are trying to do is basically the overall data that is collected. In that data, there is a lot of garbage, right? A lot of redundancy, some duplicate data. I don't know. I mean, from different sources, you collected data. For example, somebody is doing an automotive AI for driving. They might have collected lots of pictures, videos, many of them may be similar and so on and so forth, right? So a lot of them you can remove. Similarly, if you're looking at large language models for language, the search, this, that, they will take lots of articles from various places, the historical books, this, that, everything. All of that, they may have a lot of duplication. So first you remove all those duplications, reduce your data size. Also, you have to start marking those data in a more correct way, making it index based, this, that, and so on. That's a data curation process, right? When you are doing that data curation process, you read that data and you write back that data sequentially, right? You are kind of going to write one after the other. So that requires sequential write performance, all right? The third part of the AI cycle, which is one of the most important and critical, is the training, the model building and training the model. This process is a very long process in certain cases, running over multiple years, right? For example, ChatGPT, what you see today, probably the training for that ChatGPT has started many, many years back, right? So the model training itself requires a large write of data. There is an operation called checkpointing, which is usually used to do the training. The checkpointing operation requires a lot of random reads, plus doing the data writes at regular intervals, and sometimes these intervals spans over years. And overall, this is an operation where there is a lot of read-write operation required, right? Because this particular operation of model training takes a very long time, one of the key requirement for model training is endurance. For those who do not understand the endurance part of SSD, let me very quickly give you an idea that in SSD, unlike the hard drives, there is one standard problem. The problem is that if you write too many times, right? I mean, too many times is not something that you can count very easily. Too many times is a large number, but the amount of time that you keep on writing in a data center is also extremely large. So endurance becomes very important. After some amount of writes, your SSD drive will not have the capacity to hold that data. You have all seen this thing happening into those USB drives, right? You keep doing it for a few times, gone. This is an endurance problem. The data is stored in an SSD through an effect called FN tunneling, right? Where, if I assume that at least most of you have gone through the basic semiconductor training, where you know how the CMOS works, right? And possibly you know how the tunneling happens, right? where you, very high voltage, you push the electrons through the oxide into the channel in the transistor. Now, when you do something like this, you think about it, right? This oxide layer over a period of keep doing these writes is going to go away because it's a tunneling, right? It's going to puncture the oxide layer. So after a few number of writes, which is a large number, as I said, the tunnel effect will wear off the oxide and no more you can write or change the numbers. So that's called the write problem in SSDs. And that's what defines the endurance of your SSD drive. It fails few bits, fine, you will recover. But it keeps on failing. At some point of time, you take your USB out and throw it, right? That also happens on the SSD drive. So very important when you are doing an AI that you have a very large amount of endurance. Otherwise, by the time you teach your model, some of your data is gone. Your model wouldn't recognize the data or model wouldn't have got the parameters right. All right. So that's an endurance problem. And then finally, once you start the deployment of the model, what you really see or what you really need is the low latency reads, because now your model can give you the data back, right? So somebody puts a query, you really need to read the data fast. The other part is to do the same thing is metadata. There's a lot of metadata that will be created, which will be part of your model. And that is what is used to reference the actual answers. And then overall is the data computation, right? So this is your AI lifecycle and how the storage is used to work along with the AI to create this particular infrastructure, right? All right. The next part is again, I've just taken one more part of the AI cycle, which is called the inference, right? Where you get the answer. And I'm putting down a very simple system, which is called RAG, which is retrieval augmented generation. So basically, there is already certain data in your system, in your model. It understands that. And you provide some augmented data, additional data to which is more based on your company or what your purpose is and so on and so forth. And then combine these two data, like for example, LLM, you combine with your own company data and provide a system that can answer you back. For example, you might have seen almost every bank, every other organization these days, if you go to their site, on the right hand corner, you will find one small box coming up saying that I am Annie or whatever name, right? That's your chatbot. And users can write a question there. Of course, more or less, those are not giving you answers right today, but they are improving. They are improving all the time. And what they are really doing is basically they have a database here, right? They have a database here stored. And then they have a large language model, which is part of any of those search engines like Meta or Google or ChatGPT or whatever you call it, right? These two combine, what they're going to do is, so for example, you are a user, you ask a question, what was my last transaction in my account, correct? The question will search for results, the data, actual data, and then it will search. So this is how it goes. First, the question goes to a retriever system. Second, the search happens for the data. Sorry about this. You get a result out from your storage. Then you ask the LLM that how do I create my answer? The LLM gives you answer back, formulated answer, and you pass it back to the user. This entire thing has to happen real fast. You shouldn't even realize that you asked question to somebody and it took time, right? This is one of the key requirement of that particular system, right? In this, again, you see that search and result is done on your storage. And that is where I'm going to come back and say that why this storage is required and why and what we are doing in terms of computational storage. So now I'll go back to my very previous or very first cameo, whatever I did, to tell you that, there are two problems that we are trying to solve here. And that is where the computational storage comes in. What is it? As I said, first thing is that somebody is created for certain task. Like me, engineer, can't become Salman Khan on certain days, right? So, can't be an entertainer. Similarly, what we are trying to do here is that when you have a GPU and when you do not have a computational storage, you have a dumb storage, the GPU or CPU has to do the task of managing the storage. Or, for example, you asked a very simple question, where was my transaction, last transaction? The transactions database is stored somewhere in the storage. You need to pick the whole database, bring it to your CPU or GPU, ask it to search it out, and then get an answer. What is the answer? One simple line. Why can't this be done in a storage? Because storage is sitting right near to that data, and it could have given you one simple line instead of giving you 1,000 page one dictionary saying that please search your answer in here. How would you feel? Just the way you felt when I was trying to do something, right? That was not my job. Similarly, it's not CPU or DPU's job. When you ask CPU or DPU or GPU to do a job of storage management, it is going to take enormous amount of power. It's going to be very inefficient because GPU is not designed to operate data. It's not designed to work on the database management. Storage, on the other hand, which is sitting right next to the data, can do it much more efficiently, right? And that's what we do when we do this computational storage, right? What are we doing? We are moving the compute to the data. So our storage controller, our computational storage drives are actually doing the compute that should have been done by CPU or GPU otherwise, right? And by doing this, what we do is we reduce the amount of data that moves between the storage and the CPU or GPU to by an exponential degree, and thus reduce the overall system power, right? And also reduce the latency it takes to find the data out. Also, it means that now your GPU is free to do some other task. So thus improves the overall efficiency of the entire system. And how are we doing this? So we have innovative SSD controllers with acceleration engines which perform this database management tasks. And it is done in such a way that this drive fits into your regular drive space. It consumes your regular amount of power, and it still gives you the same or higher performance and does this computation. The idea doesn't look very great. How many of you think this is a very simple idea? Of course, compute should go near to data. Then why is that all the SSDs are not doing this? Big question. The main reason is, you think about it like this. There's a huge pipe through which lots of water flowing, right? Now you need to take this entire water and distribute into multiple pipes. Because the water is coming from a high force, which means also a high speed, you have only so much time to spread it across multiple things. Now, if I tell you that this water is going to come into or come in a way that there are going to be different colors. I don't know how I manage that, but assume it's going to come in 100 different colors and you have to put it in different pipes. And I am going to tell you that it is still going to come at the same speed. You will say, boss, that's not going to happen. How do I segregate those 100, right? And then put them in a different place? That's the challenge. The idea is simple. Execution is a problem. And that is where ScaleFlux has developed some of the world's most innovative computational solution, and ScaleFlux is the only company in the world today who has got a single chip computational storage available. A drive which goes into standard NVMe slot and works like an every other SSD drive and giving you these advantages, right? And we'll talk a little more about some of the advantages, because what we are creating here is efficiency. We are not reducing power. By the way, let me tell you, H100 GPU from NVIDIA, which consumes 700 watt power, I cannot reduce its power from 700 to 500. It's not possible. It's already made, right? Even NVIDIA guys can't make it. They will, as an evolution, they will, next generation, they will try to reduce the power. But I will tell you, that's what they will tell you, or any other semiconductor company will tell you that. But let me ask you this simple question. 10 years back, if you see your mobile phone, whichever mobile phone you were using 10 years back, look at the battery of that 10-year-old phone and look at your battery today. Which is bigger? Why? I mean, we are supposed to reduce power every generation, but we are increasing the power. So please do not believe that 700 watt is going to come down to 500 watts. No. 700 watts is going to go to 1000 watts, but not coming down, because we are going to increase the functionality. We are going to make sure that more and more things can be done with 700 watt power. So what we are really looking at is not bringing down the power, but improving the efficiency of every component in the system and overall efficiency of the system. And that is what ScaleFlux is doing here. All right. So let me talk about, of course, after all of this thing, I have to tell something about ScaleFlux as well. Okay. So please don't mind. All right. So what are we doing? So I'll talk about our second generation of SoC. We had two generations of FPGA based products first to prove our concept that we can really do at speed computation, right? And then we have the third generation of our computation storage drives, which use our first generation ASIC. And now this is the second generation ASIC that we are just putting into production. It's called FX 5016, and our drive is called CSD 5000. CSD 5000, CSD stands for computational storage drive, right? And the brain behind this is FX 5016, right? It is a PCI Gen 5 by 4 lane PCI Gen 5 drive, 16 NAND channels, write reduction technology, which is the key to our entire efficiency stuff. The computational engines, which can manage the database, right? For example, you can ask a query and the reply comes back. And the power efficient design. Why I say power efficient design? Because I'll show you that we do the exactly same amount of performance or higher performance as in every SSD drive in the world, and we still sit in the same slot where every other drive sits, and we still give you a computer, right? This is how we are power efficient. And the most important thing, which the very first part of that AI required, is the capacity. Today, we can proudly say that this is the highest capacity drive available in the world for SSDs. It is 256 terabyte single drive. Of course, this is not a physical capacity. What I'm talking about is the physical capacity is, even the physical capacity is probably the world's largest capacity. It's 128 terabyte in single drive. And with write reduction technology or the compression decompression that we have a 256 terabyte drive in one single drive, right? This is the capacity that we are talking about right now. To go a little deeper into the FX 5016, this is the overall architecture. What it contains is two clusters of quad CA53 cores. These are all ARM cores, extremely high performance cores, which provides a coherent system. Professor Sanjay sir clearly talked about how the coherent system is so very important, right? So that's a part of us, because if we are doing compute, the coherency around the system is a must, right? And that's why we have used this 8 CPU cores. All of them are running at 1.5 gigahertz, right? And you won't see any SSDs with this much of compute power. The reason we have this much compute power is because we are a computational SSD, right? On top of that, we have data path and compute accelerators, which is what I'm showing here, which does inline compression and decompression. The water flowing example that I gave you, this is the inline compression and decompression. So these engines, they are capable of identifying the type of data. And if it is compressible, it can compress all the way up to 4:1. That means for every 4 kilobyte data that host is writing, actual data that is getting written into the NAND flash is just 1 kilobyte. And that is how what we do is the SSD, which looks like a 4 terabyte SSD, we can allow you to write 16 terabytes of data into that 4 terabyte SSD. That's what is our solution here, right? So what it does is when you write less into the SSD, as I told you, the endurance of the SSD automatically increases, right? And I'm going to show you about certain benchmarking that we have done across the industry available other PCI Gen 5 drives and get you some data, right? So overall, with inline decom engines, we are having 24 Mbps, 16 NAND channels, right? Which gives the capacity and at a very high speed. The total dual port, high capacity, low power LPDDR5 interface. Keep in mind that while we have a lot of NAND and capacity, there's a lot of compute function that needs to be done really fast. And that cannot be done if we don't have this DDR5, right? LPDDR5 interface, dual port. And that's a key to our solution, right? Then we have dual port PCI Gen 5, which is running at 32 Gbps per lane for a plug and play NVMe 2.0 interface. I'm pretty sure that many of you do not know the SSD stuff, right? But probably we can't go into all the details. But if you have questions, we'll answer that, right? And we have a large buffer manager, which will be allowing us to do a very large IOPS while doing something called GC or a garbage collection. It's again a term which is very much required to make sure of a high endurance on the SSDs. All right. So just give you an idea about how our SSD performs against the similar type of SSDs which are available across the world. The first one is sequential read. Basically, you are reading the data one after the other contiguously, right? When you do that, there is hardly any performance difference between a drive A, B, or ScaleFlux drive. The reason being that all of them are running on PCI Gen 5. All of them can read from the NAND as high as possible, and they can supply the data. So it's like a force of data which is coming in. Everybody has the same pipe size. Everybody can push as much water they want, right? So the water quantity that can come through the pipe remains same, right? Next is sequential write. This is where the game changes. While drive A and B, as you can see, compared to them, we have 2x performance gain because we are doing the compression. When it comes to random reads, which means that you are going to read data randomly from any location in the storage. It's not going to be contiguous. Suddenly you'll read from this place or that place and so on and so forth. This is very important when there are queries and so on and so forth, right? So this is called a small amount of data, like 4 KB is the data size or the page size is what we are trying to read at a time. When you are looking at that kind of a thing, again, ScaleFlux performance is much higher, at least 20-25% gain versus the fastest available one. And when you look at the random write, this is where we are much, much higher in terms of performance, and it's a 4x performance efficiency. All right. Just to give you a perspective about how well it works in a pictorial way, performance 2x, the effective capacity that we can provide is 4x. Why? Because we can do up to 4 times compression of data, as I talked about, right? And with this, kind of performance and reduction of writes, basically the endurance of the drive goes up by up to 6 times, which is where the SSDs which are provided by us, right, can be extremely useful when you go for an applications like AI, which are going to run contiguously for a long amount of time to do training and deployment. All right. So this was the comparison of CSD 5000 with another SSD drive of Gen 5. If you compare this with hard drives which are available today, right? Currently, for example, a 2U rack has about 23 HDD drives in one rack or one array, and 22 terabyte each, right? It takes the whole array. If you compare that with ScaleFlux CSD 5000 drive, for example, it will replace the entire array with just one drive. That's how much the capacity and the performance difference that it can bring. So when you compare with HDD, absolutely, actually, there is no comparison. About a dozen HDD will be used to just get the capacity of one SSD. And performance-wise, the IOPS-wise, the amount of write-wise, there is absolutely no comparison, right? So yeah, this is what it is all about. So overall, just to summarize where we are, the CSD 5000 drives, which is from ScaleFlux, right? It gives the highest performance in the industry, the highest capacity density, and because it goes into the same slot with all these extra functions, capacity, and so on, highest power efficiency, right? Endurance, we talked about almost 6 times of what we are, and all of these combined, it means extremely high ROI. It's as simple as this. For every data storage, the cost is basically how much dollar you have to spend for every terabyte that you get, right? Or how much dollar you have to spend for every terabyte data that you're going to store. And there, obviously, if you're doing 4:1 compression, the cost is directly coming down to 25%, right? So this is what at ScaleFlux that we are doing to scale the AI infrastructure, right? Quickly giving you the idea about what ScaleFlux is. We are a company that was built to deliver the data infrastructure, founded in 2014. We are headquartered in Milpitas, California, with about 300 employees spread over India, China, and US. We are focused on storage and memory product development. By the way, I focused all my presentation on storage, while we have a very similar product and solution for memory, which is the DRAM. All right, but maybe it's some other time, right? So we are specialized in SoC, firmware, and solution level product delivery. Basically, we do our own SoCs, we do our own drives, but we do plan to start selling our ASICs as well, because there are a lot of customers who want to develop their own drives, right? We have multiple manufacturing sites to serve global customers. As you can see, all the other sites that you see, some of them are manufacturing sites and few of them are sales. All right. We are extremely well funded and strategically backed by industry leaders, which are mainly in storage domain, like SK Hynix, Kioxia, Micron, Xilinx, and AMD, as well as MediaTek. This is apart from all our private investors, right? We achieved unicorn status in 2021. And in India, we have 2 design centers. One is in Bangalore and the other one is in Pune. And we focus on completely SoC development end-to-end here, right? So overall, if you look at from the business point of view and what exactly we are trying to do, is we are trying to be the way Google and NVIDIA has taken the compute from CPU to GPU, the way Mellanox and NVIDIA has taken the networking from the CPU and put it back into SmartNICs. We are doing the same with storage. We are taking the compute from the CPUs and GPUs and putting it into storage and the memory to make sure that we can reduce the power consumption, increase the capacity, lower the latencies, and overall increase the efficiency of the entire system. All right. So with that, I think I'll end my presentation here. Thank you so much for listening. I hope that you didn't get bored. Right? All right. Questions?
A different person. So, talk about, so what about the security and the data loss?
Oh, of course, there are certain standards. There is TCL OPEC standard. We of course have to be compliant. We are compliant to security standards.
So, basically the configuration you have, right? It basically takes care of the security aspect of.
Yes.
It does, right?
Yeah, we have encryption on chip.
Okay.
And everything is taken care of. All the data that gets written in NAND, by the way, it's an industry standard requirement, the certification standard requirement that all data that gets stored on NAND flash has to be encrypted. Yeah, so we are compliant. Yeah, any other question? Sure.
So typically, these would be to serve GPUs. So that would be one of the applications.
Okay.
So for GPUs, you would have frameworkers and associated framework compression technologies already in there. So that would be to reduce the amount stress that would exist between external memory and the GPU itself. That would reduce large data density already. So
What are we going to do? Let me ask you this. I told you, right? Say, I was about to go do a dance, right? If I do the dance, you wouldn't get this presentation. Simple. Your GPU is already supposed to be doing what? Graphical processing, not compression. When you ask GPU to do also compression, right? What is it doing? It's wasting certain cycles. The data is lying there. What's the point? Right? So, of course, GPU can do it. You know, your laptop, for example, how many of you use WinZip or a 7-zip? You do. Compression. You are making sure that your CPU executes that algorithm and does a compression. Don't think it comes for free. It takes several thousands of cycles to do it. Your GPU is also doing it. There is a program. If you ask it to compress the data, it will compress the data by executing that program and then write it back. It is going to consume 700 watts power. My SSD is fitting in 25 watt power slot. I can do it in less than 15 watts. Why do you want to spend so much of watts? That is power efficiency, right? So it's not that it cannot be done. You know, we told you, right? We are doing compute in storage. We are not saying that we are doing some magic, right? GPU also does compute. We also do compute. It's the same thing. It can be done. It's just the power efficiency. Yeah.
So you need a different driver that offloads that part onto this computing.
Correct. And I'll answer one more thing. You can do that. But when you have a lot of data, right? Every time, for example, you have to get that data. Because what you have done, compression you have done. You have to get all data back, decompress it first, then only you can search. Correct? Why do you want to do it that way? When I can give a single question to my drive and tell, hey, give me this 1 byte of data. It will give you 1 byte of data. Now that if you have done the compression of the entire database, you get 4 MB of data and then you find 1 byte. Again, wastage of power. This is exactly what we are trying to minimize. Yeah, good question.
Software infrastructure is already built.
Hmm.
How are we going to change that? I mean, without, so software today expects that it will be done in the repeat.
Mm-hmm.
Drives are dumb, what you are saying.
Yes, yes.
So how are you going to,
So I completely agree. The good question.
so
Already there is a software.
without software?
Already there is a software. Nobody wants to change the software much. Completely agree. But there are switches. Most of these softwares, they are done modularly. They are not done by sequential sync. You can turn on the switch, turn off the switch, because this is something that we have already tried on with a customer. They have changed their MariaDB database with a one simple switch, and then entire thing moves from the CPU to the storage. It's not very difficult.
We have a firmware also, right?
Yeah, and so that can be done. And of course, and this other thing we have to do is that yeah, one of the reasons this has not happened that widely is because, and that's one of the drawback. Of course, I wouldn't talk about it. Who thought that I talk about the challenges of SSD? No, right? I'm talking about challenges of AI that SSD solves. Challenges of SSD, we are going to solve that. All right. So the challenge that we have is that this computational storage that interface with the CPU is not standardized. Like you have PCI, you have NVMe, you have CXL. There is a way to talk to host. Actually, the way to talk to host in terms of computational language is not well defined yet. The standard is being, under the works. When that computational standard interface comes in, you will see that everybody starts using that, right? And it solves that problem as well.
This specific application is only AI and ML, or
No. AI and ML, it's just presentation. It's one of the applications. Yes.
can this particular drive be used in consumer? For example, let's say a high-end gaming PC.
Yeah. NVIDIA has already tried out our drives, even the very first generation drive, FPGA drives, on all kinds of stuff that they do, and they have published a lot of papers and everything about that.
So this is publicly available.
Yeah, should be available. Yeah, right. Yeah, you will see some of that on our ScaleFlux website. Some of them on NVIDIA. NVIDIA is one of our partners who are working with for making sure that their GPU and our storage, right, can work with the maximum efficiency.
Even I'm more
We are
interested
using our own drive, basically.
The reason I'm more interested in this because is when you're playing games, the heat generated by the graphics card is so much
Yeah.
that the overall chassis gets heated up, and the SSD which is sitting next to it fails earlier than in a normal laptop.
So I have a two-pronged solution for that.
Despite using the cooling.
So that's why what you see, right? Once we demonstrated to our customers that we can build storage, which is much more efficient because of the compute, they're asking, boss, storage comes later. Before that, we have another layer of memory, DRAMs, which is what is executing our most of stuff, right? Why don't you make it more efficient? That's why we went into the business of doing the same stuff with the DRAMs. Yeah. So we are doing the same, we are bringing it closer to the CPU, GPU to make it even more efficient.
So we'll see if the VRAMs will get more efficient.
Yeah. Sorry. I have a question for Sajid. I'll continue.
You said you can use this drive for searching the database. System with the multiple drives, and I use RAID. And how this kind of thing works.
So the RAID part is one thing, right, where you obviously have to go your search or anything. First the RAID controller will have to take. But RAID controller doesn't have data. RAID controller is only a controller. Ultimately, it will have to send out the command. Right? Now your data might be lying in multiple bases. That's what the RAID will do, right? By default, SSDs are RAID. Because if you see the SSD architecture, right, the RAID is inbuilt with the every NAND shell. But that's the hardware level RAID. If you are talking about the software level RAID, as I said, right, when you have this command interface coming in picture, where every interface knows how to talk computational language, the command will go to every drive, and then the data will be still the same way, right? But as of now, you're right. The RAID is one of the problems, because what happens is the RAID controllers are not ready to talk to the storage in the computational state.
The next question is, how many DWPDs you
DWPD, it's a question that I'll have to get an answer, because CST 3000, we proved that because our write compression the total DWPD is much higher. Obviously, it all depends on your compression. If your data is compressible, we can do much higher DWPD. It's part of endurance also, right? So as I said, we can do up to 6 times. But it all depends on how compressible is your data. You had a question.
This is based on A50.
Yeah, it's a dual cluster with a quad core.
This by
No, RISC V
Yeah.
in this one. The ones which we are right now working, we have a mix of both.
Suppose data redundancy had one drive crashes, so we have to have the second one up and running with
Okay.
drives or
Sir already answered your question. There is a way,
okay.
right? Redundant array, right? Of identical data storage, right? So it's very important for HDDs.
Too many drives have to be plugged in.
No. So that's one of the beauty of SSDs. The SSDs are by default RAID. So usually, if your controller is good enough and powerful enough, it would be anyway writing your data into multiple flashes. Now, what you're talking about is that multiple flashes fail. That's a rare event, but it can happen. And you, for example, you're a bank. Doesn't matter whether one flash is going to fail or not. You cannot lose your data. Then what you do is then you do a system level RAID, which is what everybody does, right? System level RAID is still there, where your data is not only done. For example, you're talking about something failing. I would say, what about your complete power fails, and you're a bank, and you as a customer are trying to access the data? No, you cannot have it. Have you heard that HDFC Bank was fined big time by RBI? Yeah. What is the problem? IT problems. IT problems. IT is biggest problem. So what you are saying, the people are talking about RAID even from geographical location basis. So RAID will be done at all different levels, right? And the failure, how much failure you can sustain, it all depends on the system and the money that you want to spend. Simple answer.
Challenges.
Sure.
2 times performance and 4 times compression decompression, total 6 times performance. The data size, which is increasing for the AI, is 6 times is sufficient.
Okay, so that's why I said, right, the data size increase by the AI is a problem which everybody has to face, right? There are 2 ways of solving it. One is increasing the capacity of the drive itself, right? So that you can store more and more, because that's a cost, right? The second part, what you're talking about, is how do you handle this much? Of course, you're going to put not one drive. You're going to put so many different drives to handle all this data, right? So that's how you're going to do it. And that's how you're doing it even now with HDDs.
But then again, we add to the
Of course, we are talking about megawatts of power. This we are talking about is just 25 watts. Right? Yeah. Who doesn't have a competition now? Where are you coming from? Mars? Some of them are here. So, and I'm pretty sure that they are asking me this question. Where are you from? Marvel. Of course. Sorry, did I answer your question? Yeah, please go. Yes. When it comes to computational storage, single chip SoC solution with NVMe 2 compliance, nobody else.
Ignorance for adoption of the technology. My question was from that point of
No. So I'll tell you, right? As somebody asked here, it's very challenging for everybody to switch to computational storage and take the advantage, right? And we are a very new company. We still have to prove ourselves. There are lots of customers now, they are trying it out, right? And they are adopting it, but it's going to take time. Meanwhile, you guys enjoy. Yeah.
explain the efficiency you are getting from.
Okay. So for efficiency that we are getting from random access, that's a very good question because it's very detailed technical. I should have told at the beginning that I'm not a really SSD person. Who told me? I told you I'm not an AI guy. I'm also not an SSD. I'm SOC guy, but I'll answer your question still. Right? So the random part, the efficiency is really coming. You saw right, it's just 20%. Right? The reason is that we are compute guys. We do our metadata very, very well. And that's how we know exactly how and how quickly to find out that. Not only that, I didn't give you the other technical details about how fast our systems are running compared to all other competitors. And I work with almost entire SSD gamut, whether it's Samsung, Broadcom, Intel, Hynix, everybody we have done the drives and the controller chips. I'll tell you that we run our systems at almost double the frequency. So that's how we really manage the performance of that. Yeah. Sure.
That's one of the. So is there a body that is working on standardizing?
Yeah, of course. Yeah. So it's CXL is one body, which is as part of that itself they are coming up to do certain computational operation as part of the CXL standard itself. Right? It's coming, and then we are working with those bodies to make it even more generic, include more computational stuff, right, and so on and so forth. Yeah. All right. Looks like we're done. Thank you very much for all your questions and all. Helped me a lot. Yeah. Yeah. Thank you.